So, today we will try to see some basics related to optical aspects, so that we will be subsequently when we use will be very easily we will be able to corroborate and move forward. So, today we will look into Fresnel's law, optical fibers, some general right inputs which will be useful for us to proceed. Now, when an unpolarized light travels through the medium and interacts with the tissues, okay, what we will see is the reflection, some reflection, scattering, transmission, etc. And if we consider, okay, we will not consider scattering losses etc., but we consider only the light getting reflected and getting transmitted, then how will it right right in terms of its intensity etc., how it varies or how it change in terms of its reflection or transmission. Okay. So, there are some terms. One is when it gets reflected, we will represent it with EOR or EOT for right transmitted, and reflection RX RY TXTY, and EOI is the right input part incidence, R is reflected one, and T is the transmitted waves. Okay. So, when we know that when light incident wave comes, okay, with different polarizations, we will represent them with this vertical polarization and horizontal. Okay. We the horizontal polarization is nothing but it is in the plane of incidence, okay, and vertical polarization is perpendicular to the plane of incidence. Okay. This, so, incident wave comes in the plane of incidence, whatever polarization state equivalence means, of course, it is a non polarized light, but you can represent in terms of vertical and right horizontal. Now, the vertical one is known as let us say it is transverse, okay, and electric polarization field or right perpendicular this, and horizontal one let us say parallel, and let us assume that it is we are going to consider TE wave. So, TE wave means electrical field oscillating in the plane perpendicular to the incidence plane. Okay. So, what is that wave? What we will represent is in terms of this right vertical all components of the electrical field wave. Electromagnetic wave, unpolarized wave has multiple right polarization state, and only the vertical component of that electrical field, okay, which is oscillating perpendicular to the plane of incidence, is transverse electric wave, T wave. Okay, right. So, T wave is perpendicular, okay, remember transverse electro, and when we consider electrical field, okay, parallel to the plane of incidence, oscillating in the plane which is parallel to this. Okay. So, what will be the corresponding magnetic field direction will be perpendicular to the plane of incidence, is not it. So, it is known as TM wave, TM wave, okay, transverse magnetic polarized. So, electrical field is in the plane of incidence, oscillating in the plane of incidence, is it okay? This is the convention, right, you can change, but this is the general convention. So, whenever you refer any textbook etc., you will right, you will follow this convention, it will be easy for you to understand. Okay. And TE wave is also known as perpendicular, it is also known as S polarization. Now, the S has been derived based on, so it is a German word which represents perpendicular polarization, okay, okay, in English terms, and TM wave where electrical field is in the plane of incidence, so parallel right to the plane of incidence, parallel to the plane of incidence, that is why it is a parallel wave. Okay. And P polarization, it is represented by P polarized wave, okay, P polarized. So, terminologies, these are all terminologies. Okay. Now, if we use vector approach in order to derive the relationship between input, reflection, transmission, this if we derive this relationship, we will end up with multiple such equations at this boundary, at this point interface, okay, at this point where we consider this 0 point, we consider incoming electromagnetic wave or electrical field, then reflected, transmitted, reflection is the same as the incidence angle, transmittance will be at a refraction angle, theta 2. So, all these aspects if we consider and try to derive the relationship between these three relationship, and from there we will derive what is the reflection coefficient corresponding to this formulation is given by. So, input is EOI, reflected is EOR. So, the reflection coefficient for the T wave, perpendicular T wave is given by this form. And what is N1, N2 are? N1 is the refractive index of the incidence plane, the incidence plane. So, if I go back, I will come back to this. So, this is incidence plane through which the input is coming. So, this this is another material, material 1, material 2, this may be air, this may be glass, this may be glass, this may be air, depending upon how we. Now, here this is the material 1 with refractive index N1, this is the material 2 with refractive index N2, okay, and relationship between this and corresponding theta 1 and theta 2 etc. are known to us through Snell's law, okay, through Snell's law. So, that is so reflection coefficient corresponding to the TE wave is given by this form, N1 cos theta 1 minus N2 cos theta 2 divided by N1 cos theta 1 plus N2 cos theta 2. Similarly, reflection coefficient, this R represents coefficient, okay, corresponding to the amplitude of the electrical field. Now, the ratio of reflection divided by input for R parallel plane polarized is given by this form. Similarly, transmittance, these values can be derived. We are not going through the derivation, we are just seeing the outcome of those equations based on the vector mechanics. We will be able to derive these values. Now, there are some special cases. One, let us say theta is 0 degree, okay, theta 1 is 0. So, so obviously, when theta 1 is 0, okay, theta 2 will also be 0, and if we substitute here as cos theta cos 0 cosine 0 cosine, here we will be able to derive which is equal to 1. So, N1 minus N2 by N1 plus N2, this is R x. So, similarly, for transmittance Tx, okay, is at theta 2 is given by 2 N1 divided by N1 plus N2, okay. So, when a light comes with incidence angle is 0 degree or normal incidence, there is no reflection observed, but transmission comes into picture, reflection comes into picture. That reflection is given by N1 minus N2, reflection coefficient is given by N1 minus N2 divided by N1 plus N2. Corresponding to this, what is the reflection, amount of reflection, okay, this is the coefficient, it is based on the amplitude of the electrical field. And what is the relationship between amplitude of the electrical field and the intensity of the electromagnetic wave? It is proportional to the modulus of E square, intensity I is proportional to the modulus of the E square, right. So, reflection, from reflection coefficient we can estimate reflectance R, which is square of this reflection coefficient, right. Intensity of the electromagnetic wave is proportional to E square. Okay. Is it right? We had last class we had right described this relationship. I am not considering the factors associated, right, some of the factors related to epsilon, mu, etc. I am just, it is proportional. So, E I R reflected intensity divided by incidence intensity, right, is nothing but R, right, it is R, which is R given by this R, right. So, and this R since E square is related to reflection coefficient R, so R square, right, is given by small r square and big, right. So, we can see that if we are seeing a normal incidence, the reflection will be n 1 minus n 2 divided by n 1 plus n 2 whole square, is not it, because reflection coefficient is n 1 minus n 2 by n 1 plus n 2 for T waves, right, for T waves or TM waves, both the cases at theta equal to 0 incidence, whatever we see as the reflection is because of this Fresnel equation. Okay. Is it, am I clear? So, that is why you might have observed when we see in front of a glass window, okay, glass window is there in front of us and still we can see some reflection, is not it. We think glass window, if it is transparent, it should transmit the light as it is, but there is some reflection. What is that reflection? It is Fresnel reflection based on the reflective index of the air medium and reflective index of the glass medium will determine what is the percentage of reflection which is coming into picture. Is it okay, right? And what is the amount of transmittance? 4 n 1 n 2 divided by n 1 plus n 2 square. So, for example, if we consider one simple example just to get an idea that let us say we are considering a medium, consider a case example, right, consider a case where light is travelling okay, from air to right, and it is travelling through air and it is right incident on a tissue material, let us say a tissue, there is a tissue, okay, and refractive index, right, is let us say n 1 equal to 1 in air, okay, and refractive index of tissue material, let us say n 2 is equal to 1.35. Okay. So, what is the reflection coefficient, right, R perpendicular or R parallel at theta, normal incidence. Okay. So, there is it is a normal incidence. Normal incidence means theta is 0, right. Theta is 0 is given by n 1 minus n 2 divided by n 1 plus n 2, correct, this is given by this. So, 1.35 minus 1 divided by 1.35 plus 1, correct, and or 1 plus 1.35, I am sorry. So, that can be, oh I am sorry, there is a error in my this, it should be minus, means n 2 minus n 1, no, because R perpendicular, this will be a minus coming into picture, okay, or this answer will become minus anyway, whatever way you consider, okay. So, that is going to be minus, let us say in this case minus, 0.149 and transmittance, right, okay. This is sorry, not transmittance, coefficient of right, reflection coefficient of transmission, and corresponding R will be square of this, right, square. So, that will be approximately 0.022 or 22%, correct, 22%. Am I clear? Okay. And correspondingly, sorry, not 22%, 0.022 into 100, 2.2%, correct, 2.2%, and T, which is right, T square will be 0.978 or 97.8%, right. So, what you will see is the reflection as 2.2%. So, if the glass material, let us say I consider instead of tissue a glass material with refractive index 1.5, correspondingly the reflectivity value will change, Fresnel reflection, correct. Are you it is very easy, it is very clear as well. Now, interestingly, if you see this equation, right, what we considered, right, this equations with theta 1 and corresponding theta 2 values, the R parameter, right, sorry, reflection coefficient or transmission coefficient, they are varying, they will vary, right. And what has been found out, that interestingly it is let us say if theta is x axis is theta and y axis is power reflectance R value, okay, R value derived from previous, right, small r value, which is derived from n1, right, this equation, is not it, this equation, n1 cos theta 1 minus n2 cos theta 2 divided by n1 plus theta varies, n1 and n2 values are known, I can estimate r right value, and square of that is the reflectance, okay, that is derived here. What is observed, that as the theta changes, the reflectivity, the reflection, right, is in case of TE wave. What is the meaning of TE wave? Transverse electric means electrical field is oscillating perpendicular to the plane of incidence, okay. Correspondingly magnetic field is oscillating in the plane parallel to the plane of incidence, correct, that is TE wave. And TM wave is one which is TE is sorry, electrical field is oscillating in the plane of incidence and magnetic field oscillates in the perpendicular, right. So, if the electrical field is oscillating in this plane and or in this plane and right, interacts with this material here, what will happen, as theta changes, the reflection coefficient changes like this. In case of T wave, it changes like this. In case of TM waves, it goes to 0, which is, and then again it shoots up, and then both these values becomes equal to 1 maximum, right. So, the point, the position where theta position, where the transverse magnetic TM wave or electrical field oscillating in the plane parallel to the incidence plane becomes theta at this theta, which is known as a Brewster angle, then the reflection coefficient is 0. What it means? Let us say this is the glass surface in front of us. Now, electromagnetic wave comes, oscillates and reflects. It comes with different angle, again it reflects. It comes with another, I am talking about TM wave, okay, reflects. At one particular angle, you will not see any reflection, okay, there is no reflection. Here at this angle there is no reflection, which is known as Brewster angle. What it means? That there is no, if there is a reflection, the transmission intensity will decrease, right. So, there is at the surface itself there is a loss, something is getting reflected back, right. But if I use a Brewster angle, the reflection will be minimum, and if I use TM wave, right. If I select electric optical line or electromagnetic wave, right, light or electromagnetic wave oscillating in the plane parallel to the incidence plane, and I use angle of incidence as Brewster angle, there is no reflection, whatever light is getting coupled, it will 100% will get coupled in form of transmission signal, right. Of course, the material, when the light propagates, electromagnetic wave propagates through the material, there may be scattering, etc. So, loss may be there, but we at present we are not considering scattering, we are only considering reflection and transmittance. So, we will expect it to be transmitting complete. Am I clear? So, what it means in terms of our right, biophotonics, such applications, etc. Sometimes when we want to couple 100% light from outside to the inside, right, to the tissue, we will try to select a Brewster angle incidence, right, as well as TM wave, not TE wave, because if I select TE wave, I can see that there is always going to be some reflection coming into picture. Am I clear? Is it okay? Right. So, of course, still you may not be knowing how exactly we will use these ideas, but subsequently when we come across applications, you will be able to understand what it means, right. And the Brewster angle is estimated, of course, if when theta is so and so, TM reflection coefficient will be reflection will be R will be 0, corresponding to that, if I derive the relationship between N1, N2 and theta, it will be this relationship, okay. Tan theta is equal to N2 minus N2 divided by N1, okay, and that is theta here is known as Brewster angle, okay. So, this is one more form, right. So, if I consider n equal to 1, n1 equal to 1, n2 equal to 3.6, then for my Brewster angle is around 75, I do not exactly know this value, approximately 75, right, degree or so is the angle. If I consider let us say glass of refractive index 1.5 and air 1, then what will be the corresponding Brewster angle, right. So, just you can try use a glass and see a particular angle, your friend will not see any reflection of your image, right, reflection will not be seen at a particular angle when you start turning, right, you understood, right, approximately. Okay. So, that is a Brewster angle aspect. Now, there is another important parameter associated with this is a critical angle, right. Of course, Snell's law is very clear, n1 sin theta 1 equal to n2 sin theta 2. We can derive also using the previous all those forms, but this is the Snell's law, or n1 cos theta cos phi 1 equal to n2 cos phi 2. Okay. So, this can be derived. Now, as the incident ray angle starts changing, right, as theta as it goes, at the correspondingly the theta 2 starts varying, okay, the theta 2 corresponding to the refractive index starts varying. Now, if light is travelling from refractive index n1 to n2 such that n2 is less than n1, okay. So, light is travelling from glass to air, okay. In that case, where the refractive index of air is, let us say 1, refractive index of glass sorry air is 1, refractive index of glass maybe 1 point, let us say 1.5, let us then. So, when light is travelling like this, as this theta 1 changes, corresponding refraction angle will change, in at a particular angle of theta 1, the light will propagate will propagate along this boundary, okay, interface this. And this is exactly 90 degree to the normal, right, this to the normal, and it is known as the critical angle. So, right. So, and if we go beyond that, basically what we are trying to say, the light will reflect back, right, it will not get transmitted, right, beyond that critical angle. This idea is used for transmitting the light for a longer distance through a medium. Okay. So, that is nothing but the optical fiber idea. So, total internal reflection. So, when theta 1 reaches the critical angle theta c, what we will see that the refracted ray will be travelling along this direction, what I described in the previous line, right. Now, if my theta 1 is greater than theta c is nothing but the critical angle, this theta c is theta 2 corresponds to 90 degree. Okay. So, what is our Snell's law? N 1 sin theta 1 equal to N 2 sin theta 2, correct. Now, N 1 sin theta 1, N 2 sin theta 2. So, N 1 upon N 2, N 1 upon N 2 is equal to sin theta 2 upon sin theta 1, correct, theta 2 upon, right. Now, when theta 2 becomes 90 degree, so 1 upon sin theta 1, right, correct, no, 1 upon sin theta 1. So, basically sin theta 1 is equal to N 2 upon N 1, or theta 1 is sin inverse of N 2 upon N 1, correct, N 2 upon, right, no, yeah, clear, is not it? Am I making any mistake? No, I hope, right. So, this when theta 2 becomes 90 degree, theta 1 is known as theta critical, right, critical angle, right, that is the critical angle. We can estimate based on the refractive index known to us easily, right. And we will see that if my critical angle, if the angle of incidence is more than the critical angle, no refracted ray will be observed, okay, right, it is no refracted, is it okay. So, critical angle of incidence where theta c reached when theta 2 becomes 90 degree, okay. So, that is critical. Now, how can we use it in our basically optical fiber is, in order to transmit the light is, we use okay, maybe I will draw it and then explain it here. So, if we use, let us say, a material with refractive index N 1, okay, and surrounding it, let us say it is a cylinder, okay, let us assume simplified, it is a cylinder, okay, a tube, right, with the material with the refractive index N 1 and another material with refractive index N 2, okay, right. What we observed that in the previous case, that when light travels from the medium with a higher refractive index to the medium with a lower refractive index, at a particular incidence angle, right, there is no refraction, okay, coming into picture, correct, and all the light will get reflected, okay, accordingly. So, if let us say a light comes, right, travels, of course, right, at this is air, okay, this is air. So, here this is some theta something related to air, okay, air incident, such that at this interface, see here also there will be some small refraction because of the air medium to air medium when n is equal to 1 to another medium which is with a refractive index n 1. Okay. So, here there will be refraction and then it will, right, there will be refraction corresponding to theta, right, refractive index. Now, over here this angle, now light over here, what will happen? This is sorry. So, I am talking about this aspect over here, light comes with a certain angle, no, right. Let us say if it is greater or equal to or greater than theta critical angle, this angle is critical more than this. So, between these two medium with refractive index n 1, refractive index n 2, right, this is n 2 refractive index, correct. Are you understanding the picture, right. So, what will you expect is if it is critical angle more than that, you will see that the reflected will be maximum reflection, you will observe no refraction. So, over here light will get reflected, right, with the same angle, sorry, theta c. So, over here more than little greater than, right, theta c. So, there is another material here same with n 2 over here, right, n 2 it will reflect, it will come here. So, again there will be maximum reflection, correct. So, again light will reflect. So, it will keep reflecting at the surfaces, correct. So, this is the waveguide, okay, this is the waveguide, it guides the electromagnetic wave with minimum possible losses in terms of light is not escaping out of this, right. Every reflection ends up with no, right, transmission, it is ideally speaking, correct, right. So, all 100% reflections coming into picture, light does not escape out of this. This is possible when n 2 is greater than n 1 and incidence angle is greater than critical angle, right, equal to or greater than critical angle. Is it okay? This incidence angle over here corresponding to this incidence angle. Of course, air will decide such this angle such a way that this incidence angle is taken care, okay. Is it fine? Now, just for your reference, it is not that this is known as clade, okay, clade in terminology, and this is known as core of the waveguide, okay, through which the light gets transmitted. So, waveguide or optical fibers are the ones which can allow you to bend the light now. See, I can bend the light while transmitting. How can I bend the light? If I see, I want to, let us say light is transmitting like this, okay, along this line, it is transmitted. How can I bend this light? I can use mirror, isn't it? Or I can use a lens or something to bend the light, right, refractive index change. I will use a mirror, okay. If I use a mirror, then the corresponding the light will get reflected. So, I have bent the light, right, like this. I can use another mirror, then it bends right like this. So, by using mirrors M1, M2 I can bend the light, but in free space if I am transmitting the light in free space it becomes complex, is not it, where I want to bend the light, I want to send the light some other direction, I will have to put the mirrors right, and it becomes very complex. But same thing we can achieve with the help of optical fiber or waveguide with a material N2, this refractive index N1, light is getting transmitted through this, reflects, get transmitted, and it is bending also, right, I can bend it to a certain extent. So, this waveguide or optical fiber is right useful in such right applications. Now, some of the important characteristics of this optical fiber is, first of all, it has some numerical aperture associated with it. Some terminologies which will be very useful. So, first of all, for optical fiber, N1 is the core refractive index of core, right, refractive index of core, and N2 refractive index of clade, right, N2 is the refractive index of clade. Then theta 1 incidence at where is it? Let us say if I use just a geometry of this waveguide material with this as, then at this point where incidence, of course, there is a reflection here, we will not, I will remove, I am sorry, I will remove this, I will put here only with red, and this angle so if theta 1 is greater than theta c, then or and theta c, what is it, approximately sine inverse of N2 divided by N1 from the previous right relationship, then it will allow internal reflection, total internal reflection will be possible with this, and theta 1 greater than theta c will give you total internal reflection. In case if theta 1, if theta 1 is slightly less than theta c, slightly less than or less than theta t, what we will get is the partial reflection, correct, partially getting transmitted, partial reflection and plus partial transmission through the clade. So, this is core, this is core, this is clade. So, I am sorry. Results in transmission, correct, through clade, correct, through clade it will leak out some small amount. So, this is one aspect. The second aspect is related to numerical aperture. 1 minute, where is the formula for numerical aperture? Numerical aperture. So, here there is one formula. Why I am sorry, 1 minute, I will just maybe it is not, it should have been given. I will draw it is, I will put it, because this terminology will be very useful. Numerical aperture of a waveguide or of an optical fiber. Okay. With same thing, N1 refractive index of core and N2 refractive index of clade. Okay. So, what it means numerical aperture? Numerical aperture is basically gives the acceptance angle through which, right. So, let us say this is optical fiber with clade, right. Now, this is theta c, right, greater than theta c is the incidence, and theta c, both are theta c, correct, equal. So, but okay, over here at the interface this is 2 theta, okay, this way, and there is a refraction, because this is, let us say, n 0, this is n 1, refractive index over here is n 2. Okay. N 0 is the refractive index in, right, n 0 is the external medium, let us say R I of, let us say, external medium, maybe here in this case maybe air, okay, or external medium. Of course, it is having a less, n 0 is less than n 1 less than n 2. Okay. That is there. Okay. Then this incident, this angle, maximum angle, right, is this theta, okay, this theta, which is the maximum, right, within which, right, whatever light comes, okay, will transmit with the critical angle more than critical angle, is given by 1 by n 0, 1 by n 0, this is 2 theta. Okay. So, 2 theta 0, so theta 0 is half of this acceptance angle, 1 by 0 to n of the f or clade square minus n of the core square raised to half, right, square root of this. Okay. And numerical aperture is expressed as n 0 sin theta 0. So, is equal to this. Okay. Is it, am I okay? I am not deriving this. Okay. One can easily derive with the help of geometrical, right, equation. However, numerical aperture represents the maximum, this right, indirectly it represents maximum this acceptance angle, which will be allowed by this fiber without any transmission losses, it will get transmitted maximum. Okay. Right. So, a total internal reflection will be maximum. Okay. So, now we will try to see in the next class different types of optical fibers, some configurations, and related to some interface where when there is a core and clade interface, what is the amount of loss, etc., which comes into picture. We will try to see in the next class, tomorrow's class.